What do a skyscraper that touches the clouds, a smartphone that connects you to the world, and a rocket that travels to Mars all have in common? The answer is a revolutionary mathematical language that allows us to understand and shape the world around us: calculus. But before we can appreciate the power of calculus, let's travel back in time to a world without it. Imagine being an ancient Greek mathematician, a contemporary of giants like Euclid and Plato, trying to solve some of the most puzzling problems of your time. How do you find the exact area of an irregular shape, like a plot of land with a curved boundary? Or what about the paradoxes of motion, famously posed by Zeno of Ella? If you keep dividing the distance between 2 points in half, how can you ever reach your destination? These weren't just abstract puzzles, they were fundamental questions about the nature of space, time, and infinity. One of the greatest minds to tackle these problems was Archimedes of Syracuse. A brilliant mathematician, physicist, and engineer, Archimedes developed a technique known as the method of exhaustion. This method was a precursor to modern integral calculus and allowed him to calculate the areas and volumes of various shapes with remarkable accuracy. To find the area of a circle, for example, Archimedes would inscribe a regular polygon, like a hexagon, inside the circle. He would then circumscribe another hexagon outside the circle. The area of the circle, he reasoned, must be somewhere between the areas of these two hexagons. But Archimedes didn't stop there. He would then double the number of sides of the polygons, from 6 to 12, then to 24, 48, and finally to a 96-sided polygon. With each doubling, the inscribed and circumscribed polygons would hug the circle more and more tightly, exhausting the area between them. By calculating the areas of these many-sided polygons, Archimedes was able to trap the area of the circle between two very close values. This allowed him to approximate the value of pi to an accuracy that would not be surpassed for centuries. Archimedes used this same method to find the areas of ellipses and parabolic segments, and the volumes of spheres and cylinders. His work was a monumental achievement, but it was also incredibly laborious. Each problem required a new and ingenious application of the method of exhaustion. What was missing was a universal tool, a systematic method for solving all such problems. For centuries, these problems remained largely unsolved. The methods of the ancient Greeks were ingenious, but they were also cumbersome and lacked a unified approach. A new way of thinking was needed, and it would emerge from a period of unprecedented intellectual ferment, the scientific revolution. Starting in the 16th century, a new generation of thinkers began to challenge the long-held dogmas of the past. Nicolaus Copernicus proposed a heliocentric model of the universe, placing the sun, not the earth, at the center of the cosmos. This was a radical idea that would have profound implications for our understanding of the universe and our place in it. A generation later, Johannes Kepler, using the meticulous astronomical data of his predecessor Tycho Brahe, discovered that the planets do not move in perfect circles, as had been believed for centuries, but in elliptical orbits. He also discovered that the speed of a planet changes as it moves along its orbit, moving faster when it is closer to the sun and slower when it is farther away. Meanwhile, in Italy, Galileo Galilei was using the newly invented telescope to make a series of stunning discoveries. He saw mountains on the moons of Jupiter, and the phases of Venus. His observations provided powerful evidence for the Copernican model, and further undermined the authority of the ancient philosophers. Galileo also made important contributions to the study of motion, showing that the speed of a falling object increases at a constant rate. The discoveries of Copernicus, Kepler, and Galileo revealed a universe that was far more complex and dynamic than had ever been imagined. The world was not static, it was in a constant state of flux. To describe this ever-changing universe, a new kind of mathematics was needed. A mathematics of motion, of change, of infinity. The stage was set for one of the most brilliant inventions in human history. Enter our two heroes, Isaac Newton in England, and Gottfried Wilhelm Leibniz in Germany, two of the greatest minds of the 17th century, who would independently invent calculus. Isaac Newton, a towering figure of the scientific revolution, was a man of intense focus and almost superhuman intellectual powers. Born in Woolsthorpe, England, in 1642, he would go on to become a Fellow of Trinity College, Cambridge, and the Lucasian Professor of Mathematics, a chair he held for over 30 years. Newton's curiosity was boundless. He was driven by a desire to understand the fundamental laws that govern the universe. He was obsessed with the motion of the planets, the path of a cannonball, and the falling of an apple from a tree. It was during the Great Plague of 1665–1666, when Cambridge University was closed and Newton was forced to return to his childhood home, that he had his Annus Mirabilis, or Year of Miracles. In this single year, he made groundbreaking discoveries in optics, gravitation, and most importantly for our story, mathematics. To understand the motion of the planets and the laws of gravity, Newton realized that he needed a new mathematical tool. He needed a way to describe quantities that were constantly changing or flowing. He called these changing quantities fluents, and their rates of change fluxions. This was the birth of Newton's version of calculus. With his method of fluxions, Newton was able to develop his three laws of motion and his law of universal gravitation. These laws, published in his monumental work, the Star Principia Mathematica Star and United, would become the foundation of classical physics and would dominate the scientific world for the next 2 centuries. Newton's calculus was the key that unlocked the secrets of the cosmos, allowing him to explain everything from the motion of the tides to the orbits of the planets. Meanwhile, across the English Channel, another brilliant mind was independently developing his own version of calculus. Gottfried Wilhelm Leibniz, a German polymath, was a true universal genius. A philosopher, scientist, and diplomat, Leibniz made significant contributions to a wide range of fields. Leibniz's path to calculus was different from Newton's. While Newton was a physicist, obsessed with the motion of physical objects, Leibniz was a philosopher, interested in the underlying principles of logic and metaphysics. He was a master of symbols and notation, and he believed that a powerful and intuitive notation was the key to unlocking the secrets of mathematics. In the 1670s, during a stay in Paris, Leibniz began to develop his own version of calculus. He introduced the integral sign s as an elongated s for summa, the Latin word for sum. He also introduced the d notation for differentials, such as dx and die, to represent infinitesimal differences. This notation proved to be incredibly powerful and versatile, and it is the notation that we still use today. Leibniz's calculus was more abstract and formal than Newton's, and his notation was more elegant and intuitive. This made it easier for other mathematicians to learn and use calculus, and it helped to spread the new mathematics throughout Europe. So, who invented calculus first? This question ignited one of the most famous and bitter disputes in the history of science. For years, a fierce rivalry raged between Newton and Leibniz and their respective followers, each claiming priority for the invention of calculus. The controversy began in the late 1690s, when some of Newton's followers began to accuse Leibniz of plagiarism. They claimed that Leibniz had seen some of Newton's unpublished manuscripts during a visit to London in the 1670s and had stolen his ideas. Leibniz, for his part, vehemently denied the accusations and insisted that he had developed his version of calculus independently. The dispute escalated in 1712, when the Royal Society of London, with Newton as its president, established a committee to investigate the matter. The committee, which was heavily biased in favor of Newton, concluded that Newton was the true inventor of calculus, and that Leibniz was guilty of plagiarism. Today, however, historians of mathematics are in universal agreement that Newton and Leibniz developed their versions of calculus independently. Newton developed his method of fluxions in the MID-1660S, but he was hesitant to publish his work. Leibniz, on the other hand, began working on his version of calculus in the 1670s and published his first paper on the subject in 1684. While the priority dispute was a dark chapter in the history of mathematics, it ultimately had a positive outcome. The controversy helped to publicize the new mathematics and to stimulate further research. And today, we recognize that both Newton and Leibniz made independent and equally important contributions to the development of calculus. Newton gave us the physical intuition, while Leibniz gave us the elegant language. Together, they had created a tool that would change the world. So, what exactly is this calculus that Newton and Leibniz invented? Let's start with one of its two main branches, differential calculus. And at the heart of differential calculus is the concept of the derivative. The derivative is simply the instantaneous rate of change of a function. It tells us how fast something is changing at any given moment. Think about driving a car. Your speed is not constant. You speed up, you slow down. You stop at traffic lights. Your speedometer tells you your instantaneous speed, the speed at that very moment. That's a derivative. It's the derivative of your position with respect to time. But derivatives are not just about speed. They are everywhere in the world around us. The rate at which the temperature changes throughout the day, the rate at which a company's profits grow or shrink, the rate at which a disease spreads through a population. All of these are examples of derivatives. To understand the derivative mathematically, we need to introduce the concept of a limit. A limit is the value that a function approaches as the input, approaches some value. The derivative of a function at a particular point is the limit of the average rate of change of the function, as the interval over which the average is taken becomes smaller and smaller. This is expressed in the famous formula for the derivative, f equals lim 0 fx plus h f x h. This formula may look intimidating, but it is simply a mathematical way of saying that the derivative is the instantaneous rate of change. But the derivative is much more than just a way to measure speed. It's also a powerful tool for optimization. In many real-world situations, we want to find the best way to do something. We want to maximize a value, like profit, or minimize a value, like cost. This is where the derivative comes in. By finding where the derivative of a function is equal to 0, we can find the points where the function reaches a maximum or a minimum value. At these points, the slope of the tangent line is 0, meaning the function is momentarily flat. This has countless applications in the real world. For example, a company might use calculus to determine the optimal price for a product to maximize its profit. An airline might use calculus to determine the optimal speed for a plane to minimize its fuel consumption. And a doctor might use calculus to determine the optimal dosage of a drug to maximize its effectiveness while minimizing its side effects. Let's take a simple example. Imagine you are a farmer with a limited amount of fencing, and you want to create a rectangular enclosure with the largest possible area. You can use calculus to find the dimensions of the rectangle that will maximize the area for a given perimeter. By setting up a function for the area in terms of one of the dimensions and finding where the derivative is 0, you can determine the optimal dimensions for your enclosure. The derivative also gives us the slope of the tangent line to a curve at any point. The tangent line is a straight line that just touches the curve at that point, matching its direction perfectly. This simple geometric idea has a surprisingly useful application: linear approximation. If you zoom in far enough on any smooth curve, it starts to look like a straight line. The derivative gives us the equation of this line, which we can use to create a linear approximation of the function. This means we can use a simple straight line to approximate the values of a much more complex function in a small neighborhood around a point. This is the basis for how computers and calculators can perform complex calculations with incredible speed and accuracy. For example, when your calculator gives you the value of the sine of an angle, it is not actually calculating the sine function directly. Instead, it is using a pre-programmed linear approximation or a more sophisticated polynomial approximation to quickly and accurately estimate the value. Linear approximation is also used in many other fields. In physics, it is used to simplify complex equations and to model the behavior of physical systems. In engineering, it is used to design and analyze structures and to control the behavior of machines. And in computer graphics, it is used to create realistic images of curved surfaces. Now let's turn to the other main branch of calculus: integral calculus. If the derivative is about slicing things into infinitesimally small pieces to find a rate of change, the integral is about adding up those pieces to find a whole. It's a tool for accumulation. The integral allows us to solve a problem that had puzzled mathematicians for thousands of years: finding the exact area of an irregular shape. By dividing the area under a curve into an infinite number of infinitesimally thin rectangles and summing their areas, we can find the exact area under the curve. This is the concept of the Riemann sum, which is the foundation of integral calculus. But the power of the integral goes far beyond finding areas. It has countless applications in the real world. For example, if you know the velocity of a car at every moment in time, you can use an integral to find the total distance it has traveled. If you know the rate at which water is flowing into a reservoir, you can use an integral to find the total volume of water in the reservoir at any given time. In physics, integrals are used to calculate the work done by a force, the center of mass of an object, and the moment of inertia of a rotating body. In economics, they are used to calculate the total revenue generated by a company, the consumer surplus in a market, and the Gini coefficient, a measure of income inequality. And in probability theory, integrals are used to calculate the probability of an event occurring within a certain range of values. But the most amazing discovery of all was the deep and beautiful connection between the derivative and the integral. This is known as the fundamental theorem of calculus, and it is one of the most important theorems in all of mathematics. The fundamental theorem of calculus comes in two parts. The first part tells us that if we take the derivative of an integral, we get back the original function. In other words, differentiation and integration are inverse processes. They undo each other in the same way that addition and subtraction, or multiplication and division, undo each other. The second part of the theorem gives us a powerful tool for calculating definite integrals. It tells us that to find the area under a curve between 2 points, we don't need to go through the laborious process of summing up an infinite number of rectangles. Instead, we can simply find an antiderivative of the function, a function whose derivative is the original function, and evaluate it at the two endpoints. This was a revolutionary idea that unified the two branches of calculus and made it an even more powerful tool. It transformed calculus from a collection of clever tricks into a systematic and powerful method for solving a wide range of problems in science and engineering. The invention of calculus unleashed a tidal wave of scientific and technological progress that continues to this day. In engineering, calculus is the bedrock upon which modern civilization is built. It is used to design bridges that can withstand the forces of nature, to build skyscrapers that touch the clouds, and to construct dams that can hold back entire rivers. Civil engineers use calculus to analyze the stresses and strains on complex structures, ensuring their stability and safety. Mechanical engineers use it to design and optimize everything from engines and turbines to robots and machines, and electrical engineers use it to analyze and design electrical circuits, to model the behavior of electromagnetic fields, and to develop new communication systems. In physics, calculus is the language of the universe, from the motion of the smallest subatomic particles to the expansion of the entire cosmos. The laws of physics are expressed in the language of calculus. Newton's laws of motion, Maxwell's equations of electromagnetism, and Einstein's theory of relativity. All of these are formulated in terms of differential equations, a key component of calculus. Calculus allows physicists to model and understand a wide range of phenomena, from the flow of fluids and the transfer of heat to the behavior of waves and the properties of materials. It is an indispensable tool for any physicist who wants to explore the fundamental laws of nature. But the impact of calculus doesn't stop there. It's also at the heart of the digital world we live in today. Every time you watch a movie with stunning visual effects, play a video game with realistic graphics, or use a GPS to navigate to your destination, you are witnessing the power of calculus in action. In computer graphics, calculus is used to create and manipulate curves and surfaces, to model the interaction of light and shadow, and to simulate the motion of objects. The realistic animations you see in movies and video games are all made possible by the clever application of calculus. In the field of artificial intelligence, calculus is the engine that drives machine learning. Machine learning algorithms use calculus to learn from data and to make predictions about the future. For example, when you use a spam filter to sort your email, you are using a machine learning algorithm that has been trained with calculus to distinguish between spam and legitimate email. And when you use a GPS to find your way, you are using a system that relies on calculus to solve a complex set of differential equations that describe the motion of the satellites orbiting the Earth. Without calculus, there would be no GPS, no machine learning, and no computer graphics. Even in medicine and biology, calculus is a powerful tool for understanding the complex processes of life. It is used to model the growth of tumors, to analyze the flow of blood through our bodies, and to design new life-saving drugs. In epidemiology, calculus is used to model the spread of infectious diseases. The SIR model, which stands for susceptible, infected, and recovered, uses a system of differential equations to predict how a disease will spread through a population. This allows public health officials to make informed decisions about how to control an outbreak and to allocate resources effectively. In pharmacology, calculus is used to model the concentration of a drug in the body over time. This allows doctors to determine the optimal dosage and frequency of a drug to maximize its effectiveness while minimizing its side effects. And in medical imaging, calculus is used to reconstruct images from the data collected by MRI and CT scanners. These complex algorithms, which are based on the principles of calculus, allow doctors to see inside the human body with incredible detail and to diagnose a wide range of medical conditions. From the ancient Greeks to the modern world, the story of calculus is the story of humanity's quest to understand the universe. It's a language that has allowed us to build a better future, and it will continue to shape our world in ways we can only imagine.